Hi everyone, in this video I will be starting with first profile, that is the velocity profile in a laminar pipe flow, and velocity profile is this one. So keep this thing in mind that we can have the different variable names while we use the UDF. So it will be a most convenient type of the variable name which we are going to define. So these are some variables. This is a constant value. This is radius, or you can say this is equal to height, and this is the radius which is varying from location to location, like it is varying from here to there. Okay, so the confirmation of so what we are going to do is that after applying the velocity profile using UDF, the velocity should attain the fully developed profile in the very beginning. Means that from very beginning we should be seeing the U maximum at the inlet of the pipe. So if the U mean is 1, so the U maximum which should be here should be equal to 2. So this should be seen in the very beginning of your geometry or the computational domain. Otherwise, you know that if you start with a uniform flow, it will take some length of the pipe for make the flow to be fully developed. This can be like 1000 meters if the Reynolds number is 2000. So this is very long length. Okay, so start with the boundary conditions and the material properties. So the length of pipe I'm fixing here for both cases at 1 meter. So because the length does not matter here, as we are providing the fully developed flow, so that's why the length is kept very short. And the radius is 0.05 and diameter is 0.1. So you can say that L by D. So you can say that the L by D is equal to 1 by 0.1 is equal to 10, which is very short length for these type of flows. And also I assume the values. So basically Reynolds number should be meshed. So I intended to keep the Reynolds number is equal to 100. So I put the density is equal to 100. Viscosity as 0.1, or I can calculate viscosity from Reynolds number, and the mean velocity is 1 meter per second, and the diameter is double of the radius, so which is equal to 0.1. So we get the Reynolds number equal to 100. And as I told you, this flow will be modeled as axisymmetric, means that we are solving this problem in polar coordinates. And so I will be making domain only half, but in the case of channel this will be the complete domain. So this half domain is like from this location to this location. Okay, so here is a 0 and here radius is 0.05. So this is the whole scenario of the problem. So this is a mesh file, but I decided to also show you that how to make the geometry. This is very simple step, and I will do that thing inside the ICM CFD. So inside ICM CFD and also meshing in ICM CFD hexa. So this is the profile that we are going to use. And also I found out that in the new versions, there's no need to install Visual Studio, which is a very good thing to have in your computer on your Windows. But if you don't have, you can still use the UDF by compiling them using the built-in features inside the Fluent. So this is the built-in compiler in the Fluent. Okay, so after solving this case, the velocity profile looks like in this way. This is a half geometry, so that's why we are getting the half profile. But if you want to make it full, so you can do it inside the Excel. So you can just copy below the position, so the half portion will be negative side. So you have to just do one thing, that you have to make the coordinates minus values on the bottom side, and you will get the same values for the velocity. So this will make a full profile. And these are results. So you can see from very beginning, you can see that we have the maximum velocity is equal to 2, and for the pipe this is the case. And similarly for the flow in channel, closed channel, the same thing which is here. Only thing is that we are modeling the half of the length of the height. So instead of the 0.1 meter, we are only modeling again the same dimension as a pipe. But the thing is that here, the bottom wall is now taken as wall. This is not axis. And the height of domain is 0.05. But the definition of hydro diameter, which we should be using for the any case other than the circular pipe, because circular pipe has the diameter and halo diameter exactly same. But in the case of the rectangular shapes or square shape, we don't have any diameter type of thing. So that's why we use the halo diameter. The definition is that it's a ratio of 4 times area divided by perimeter. But for 2D case, it is known in the literature this is equal to the twice of the height. So it's a 0.1 again. So again, 0.1 velocity, mean velocity is the 1, and density is 100. Viscosity is 0.1 Pascal second. So again, Reynolds number is 100 for this case as well. And this is the mesh, but this time the mesh is graded on the both sides. This is the UDF, and this is a velocity profile again at some location in the channel. This is the velocity vectors and the velocity contours. Okay, so we start with the first case, and I will be starting with the ICM CFD. So ICM CFD. Okay, so the radius of pipe is 0.05. So I will be making one point at exactly 000. Second point 8.05. So question arises why we are doing the things in the Y. No, why not in the R? So the thing is that this is the things will be understood by Fluent. So when you give the mesh which we create in XY, but we select the solver as axisymmetric, so it would automatically change the coordinates from X to axial and Y to radial. But the only thing requirement is that the axis should be on the x-axis and other dimension should be on the y-axis. So that's why this axis should be exactly on the x-axis if this is a pipe. If this is a hollow pipe, then this axis will be imaginary line, and then you have to model the two walls, bottom and the top wall. Okay. So the second point, it x is equal to 1 and the y is equal to 0.05, and fourth point at x is equal to 1 and the y is equal to 0. So we have the 4 points, and now create lines. So you can put the names also. This is the axis. So the axis is over here. Then we have inlet. Inlet is over here. And then the wall. So wall is on the top side because axes are in the middle. And outlet is at the outlet, which is over here. So now we just made the geometry for the pipe, only half of the dimension. This is the axisymmetric case. So only half dimension. So you can save this project and put the name as pipe. And I will be creating new folder in E. And this one is like a pipe and channel. Okay. This is a pipe case. And one more thing is that which I will also discuss in the coming videos, that the UDF should be the same folder where you have the mesh file or your case file for the Fluent. Okay, so I will be doing the same, everything in the one folder. Okay, now you have to make the blocking. Blocking is used for making the hexa meshing. So the name of this whole control volume I'm going to put is fluid. You can put the water or air, whatever you like to put, but it should not be any name other than the any name. It can be any name, but only that you should not be putting the solid name, because solid is only reserved for the solid bodies. Okay, and change type to 2D planar. This is a 2D planar case, and apply. So now we have the one block which you can see in the black color. So these are the edges, and these corners are the vertices. So correspondence is very simple. Geometry has points and curves. So for points we have the vertices, which you can see here also, and for curves we have edges. So you have to associate first 4 vertices for the 4 points one by one. So you have to click left button continuously. So this will select the vertex and then point. And then second option is to associate edges to curves. So again you have to select with the help of your left button, your middle mouse button, and once again you click, it will go to second option, and then again it will confirm the selection. Okay, so to confirm this thing, you can hide geometry and you can see that colors of vertices, they are changed to red and color of edges are changed to the green. This is the confirmation. Okay, so now we have to define the number of cells here. So number of cells will be around 20 and I will be put some grading on the upper wall because wall will be developing the boundary layer. This is the main requirement here. So I'm going to make this as a geometric one because geometric one will make the grading or the mesh refined on this side, but geometric 2 will make the mesh refined on the other side. And the first cell height I'm going to put is, this is right now is a point 0026. So I'm going to put the one order of dimension less. So this will be point 0001. So let me check. A ratio is a 1.2. Okay, there is an error here. This is a double decimal here. So remove one and apply. Okay. So 1.2. Okay, geometric 2 and let me define again 0.001. Sorry, this should not be here. This should be on the side number 2. This is geometric 2. So 0.001 and 1.2. Okay, now let me check the pre-mesh also. This pre-mesh looks like in this way. So, okay, so sometimes this may not work. So we have to make it first uniform and then come back to the geometric 2. So uniform and then again make it geometric 2. Okay, this is not taking the command. I don't know why. So we have to select the edge again and put the value as a 0.001 and 1.2 and apply. Okay, so I just closed ICM CAD and again open the ICM CAD with a file and now it seems to be working here. So I'm going to select the geometric 2 here. So, and I will be putting the sizing on the spacing number 2. So 0.0000 maybe 2 and 1.2. So it is taking the size as this one. So let me check the mesh. Okay, here on the lengthwise I will be defining uniform spacing. So let's define maybe 100. So it again I will be recommending that you should be running the mesh independence test here. So you can make the different meshes here and there. Okay, so select the geometric 2 here and maybe we can work with the bigeometric. This should work nicely. So right click and recompute. At least we should be having some elements on the bottom side also. Let's make it 30. So relative spacing should be not selected. So here I'm going to put the 10 power minus 3. Okay. And then 10 power minus 4, but 5 10 power minus 5 and right click here and recompute. Okay, so I think this spacing will not be enough. So I am going to have the spacing at 0.301 and right click and recompute. Okay, this seems like, okay, let me check the geometry size. So geometry size, the radius should be 0.05. This is okay. So let me again do it. So maybe we can make the number of cells as 40. Okay, so I come up with the 60 cells around the length and 20 nodes along the radius, and this is by geometric. First cell height is 0.0005 and the ratio is 1.1. You can also make it slightly maybe less. So next step is to convert this mesh into unstructured mesh. So right click here and convert to unstructured mesh. Okay, after this you have to output mesh. So select the solver and boundary conditions on the edges. Axis will be axis. So this is going to be the axis. And the inlet is the velocity inlet. So velocity inlet here. And outlet is the pressure outlet. And wall is a wall. So select and accept. Now you have to export the mesh file and make sure this is the 2D export. So select the option as 2D and this is the pipe. So put the name as a pipe and click on done. Okay, now open Fluent and make sure that the 2D option is selected and number of cells are very low, so that's why I'm using only one core from my 4 cores. And working directory should be selected properly. So from here browse for your working directory and it should be over here. So select the folder and now you can click on the mesh. So mesh file is inside the folder, so you can select the mesh file also and click on open and click on start. And one more thing is that I need to copy the UDF from here to the working folder, which is right now in the E, and this is the cylinder and channel, pipe and channel. So paste the file here. So all files right now are in the same folder, and also I'm going to copy these files for channel here. And also one interesting thing, that can directly use this mesh file for the channel. Only thing I need to I need to change is that the axis should be made now as a wall. Simple thing. Okay. So we have this mesh is over here. Okay. So the first thing is that we should be selecting the solver as a 2D axisymmetric. And boundary conditions, they have taken the proper names as they come from directly from the ICM CFD. So just confirm, axis is axis, inlet is inlet, outlet is outlet, wall is a wall. So same thing. Okay. This is the velocity inlet, this is the axis. So at the inlet, I am just defining for a time being the 1 meter per second. So I will show you this thing. So after doing this thing, then the material properties are density is equal to 1000 and viscosity is a 0.1. So density is 100 and viscosity is a 0.1. So change, create and close. Again you have to save your case file. And in the methods, just keep the default settings. In the controls, keep the default settings. In the monitors, because it's a laminar flow, so also you should make sure that the laminar flow, yes, this is the one important thing, the models should be selected by default is SSTK omega. So change this to laminar flow and click on OK. And for laminar flow, the flow convergence goes to very low values. So I'm providing the 10 power minus 20 so that the solution should not be stopping before I want to stop it. So I will stop based on the number of iterations. Okay, and so I will initialize from inlet with a 1 meter per second velocity at the inlet, and I will run calculation for like maybe 200 iterations and click on calculate. Okay, now let me check the solution. And velocity, I think velocity will not be fully developed. So this is the problem. You can see velocity magnitude is 1.99, but that is maybe over here. So Now let me display the vectors. So you can see initially the velocity is not developed here, and eventually this developed here, but at the outlet. So and you can also display the complete file. So you have to go to the views, and from here select the axis and click and apply. So you can see the full pipe or full cylinder. So you can see the flow is starting to develop here. So this is the problem here. Okay, now we have to compile the UDF. So I will go to the, so inlet condition is, you can see, again you can confirm this is a constant value. Okay, this is a constant value, you can see here. And finally it start to develop into fully developed flow, but that takes some length. Okay, so I will go to the customization, parameters and customization, and from here right click on the user defined functions and click on compiled. So I will be adding the UDF, this is a velocity profile for the pipe. Okay, and put the name as a velocity profile for pipe. So because we are going to compile the both UDFs for channel and for the pipe in the same folder, so default name is a library UDF, so lib UDF. So don't have the same names because these are two different UDFs. And I will use the built-in compiler. So I didn't install the Visual Studio, that's why I'm using the built-in compiler. And click on build. Okay, so you will see some messages over here, and click on load. And now you have to go to back to the boundary conditions, and from here you have to select your UDF. So the UDF is over here. You can also use the parameters, you can also use the expressions. Apply and close. So again you can run calculation. Okay, one thing I would be recommending here is that because the coupled solver is making issues here, so I would recommend that you should go with the simple. Okay, go with a simple method. And also I will go back to my residual plots. From here I will be showing the axis. Okay, so and for the y-axis, so basically I'm not able to see the things properly. So okay, and okay, so click on now calculate again, but this time I will initialize solution from inlet with the same boundary conditions. Okay, and then you have to solve the case again in a similar way and calculate. Maybe we need to provide the more iterations here for simple solver, because simple solver will take more iterations compared to coupled solver. So maybe the 1000 iterations will be enough. So values are going down to tempo -13, -17, -16. You can see -13 and -17 are the values for x and y velocity. So we can stop here and see the velocity contours, velocity vectors. So now you can see the flow is fully developed from the very beginning, and you can make it banded, and you can choose the color map as 30, and you can also now make the few things here. So I would recommend that BGR is a good thing here, the blue, green and red. In some cases arrow is also a good option, but not for this case. So BGR is a good way to display your contour plots. So first thing, you can confirm the velocity is maximum at the center, which is 2 meters per second in the very beginning. And this is the use of the profile, that it will make it will apply the fully developed flow in the very beginning of geometry. So you can shorten your geometry or your domain. Okay, one thing. Second thing is that you can plot the XY plot for the velocity profile. So we will position the y-axis, the velocity on the y-axis. So this will be along the y-axis, and what we are going to plot, we are going to plot the axial velocity. And we are on the line, so line can be anywhere. So I'm going to put the line on the middle. Okay, so make the line, and this line is going to be at the x is equal to, let's say, 0.5. This is the midway. So 0.5. This is from 0 to 0.05. Create. And so you can see that we have the velocity profile like this. So you can change the axis. So for y-axis, you can put it like from 0 to 0.05. This is the dimension for the pipe radius. And velocity is changing from 0 to 2 meters per second. This is 2 meters per second on the axis. And you can also change the units. So you can make them as floating with the 2 decimal places, or maybe 3 decimal places. 2 is enough. And similarly for the y-axis, you can also do the same thing. 0 to 2. This will like this. And also you can add the lines also. So from the curves, add the line. You can change the color also. Any color you want. You can also change the color of these dots or the markers, and you can also change the size of marker. You can also change the width of the line. So let's say from 2 to make it 4, like this. Okay. So this is completely for the velocity profile application for the pipe. And let me discuss the UDF. So UDF is over here. Okay, so let me briefly explain. This is not a UDF course, but I will be explaining these things very briefly. This is an important command, and it should be included in the every UDF. Okay, and then we define the y minimum. This is the 0, and the y maximum is the radius, which is 0.05, and the u mean velocity is the 1 meter per second. This is the built-in macro command that we just take it and apply. So this is the name of the your profile. This is the axial velocity profile. This is t and I. This is for the dimensions. Okay, so we define the one vector x and d. This is depending on the number of nodes or number of cells on that particular boundary condition. So we define the real y, real h. So simply put here, this is equation is u maximum, which is 2 times the u mean, and in the bracket this is 1 minus r square upon r square. So this r is denoted by the h, which is y maximum minus y minimum. So this will give you the 0.05 minus 0 is equal to 0.05. So this can be different value. This can be, maybe you are starting from not from the 0. This may be concentric pipe. So we can be starting from the, let's say, 0.1, and the top boundary is a 0.2. So again, the height is equal to, our radius is equal to 0.01, 0.1. 0.2 minus 0.1 is 0.1. That's why I put things in this way. And then you have to ask the fluent for giving you the centroid. So this is the loop for your velocity profile along the different cells along your boundary. So, and the u maximum is going to be the 2 times the u mean. This is for the pipe. So this is I put it wrongly here. This is the 1.5 into the u mean, the 2 into u mean. Okay, so this is like 1 minus power of y, which is 2 here. So power of y is 2. So y is basically is the radius. So radius squared divided by power of h. So power of h is the capital R. So this is the r square multiplied by the 2 into u mean. So this is the profile we are applying along the different locations of your mesh on the inlet boundary condition. Okay, but the boundary the UDF which we used here is basically has the 2 into u mean. So let me make the correction here. Okay, this is the UDF we are going to apply. Okay, so with this, we completed the part of the velocity profile application for the laminar flow in a pipe. So in the next video, we are going to apply the next profile, that is the velocity profile in the channel, but I will only solve the channel flow with the closed, means that the two walls on the top and bottom. And third case, you will be solving yourself. So you have to modify UDF little bit. Okay. Okay, so this is the end of this part.